But there is one practical, or we'll say a major practical issue in this. This is the following. So let's say here, remember, I have to compute the PSD of this output data B, and remember, path spectral density, we do that by taking expected value of magnitude squared of the discrete time Fourier transform. Essentially, we need to compute the discrete time Fourier transform, take magnitude squared of it, and blah blah blah. So the issue is in computing this guy itself, because if I take discrete time Fourier transform, how do you compute? What is the expression for this? Remember? Summation? The x of n, but what is the limit of the summation?
0 to infinity.
And then?
E power minus j omega n.
That's all. So now you see, I have omega, which is a continuous variable. So in principle, if I had to measure this, I have to measure it for all possible values of omega. So that is one problem. So I'll say omega is continuous, right? I mean, see, it's all time shift, right? I mean, there is nothing as minus infinity. We are dealing with causal systems. So the second, what do you think is the second difficulty here? I mean, this is, yeah, omega you have to do for all thing. What about this guy? Yeah, in principle you have to do it for infinite data, right? So looks like I have to have an infinite record length. So these two are practical difficulties in finding this discrete time Fourier transform. And of course, if, no, we don't need to worry if there is problem. We should be in fact happy because we have something to do. So what do you think is a natural solution for the first problem?
Discrete omega.
Yeah, instead of computing this for all possible values of omega, you do the same thing as we did in sampling. You compute only at discrete frequency points. So let us say this is my frequency axis omega from 0 to 2 pi. This is, let us say, the spectrum something. Instead of finding for all values of omega, let us say I decide to choose at n discrete points. So what are the, n discrete points like this, right? Say something blah blah blah. So like any sane person will do, I'll take it with uniform spacing. And what will be the, let us say, this spacing now? 2 pi by n. Fine. So instead of doing for all omega, I'll do at omega, which is k times 2 pi by n, where k goes from 0 to n minus 1. N points of this. Reasonable? And what do you think is a simple solution for this fellow? In principle, I want to have infinite data. In practice, what can I do? Yeah, you can only have a finite. You try to make it large, whatever, but you decide that, hey, I can't have infinity, I will have only finite data, right? So I'll say it's a finite, you choose this to be a finite record length, I'll say record length is NR. Okay. So let's see what happens when I make these two changes to this equation. So let me take this once. So this is the transform. Similarly, if I were to compute, reconstruct the sequence from the Fourier transform, what do I do? This is the forward transform. What is the inverse transform? See, same thing we have to do, right? Remember that any transform of frequency calculation is basically finding inner product of the signal with a complex exponential. Inner product is taking the product and integrate it, that's it. So here I am doing with x of n. So here I have to do with x of e power j omega. I have to integrate with e power j omega n. And this is, a continuous variable, so I integrate instead of summation d omega from, again, let us say minus pi to plus pi, because it is spanning a periodic thing of 2 pi. And remember, anytime you do this with omega integration, there will be a scaling factor of 1 by 2 pi. So this is what it is. So here we are making two changes. one is I replace omega with a discrete variable k 2 pi by n. Second is I change this upper limit of summation to a finite value. So this basically changes to, or I'll copy it and put it maybe, or it's okay, I'll write it. So this changes to n equal to 0 to nr minus 1, the total of nr samples, that is the record length, e power minus j. I no longer have a continuous omega variable. At what points of omega I am computing? 2 pi. Yeah, 2 pi, k times 2 pi by n times, we'll come to that. I'm just saying, I mean, it's up to you, right? Point is again, it's all up to you. This is the Fourier transform. At what all points you want to compute, it's up to you. We'll see in detail later, but yeah. So similarly, I'll write the reverse thing also quickly. So this is 1 by 2 pi, and remember this now x of k, okay? Because I no longer have omega, it is k 2 pi by n. The variable is k. Fine. So similarly, I can rewrite this. So x of e power j omega becomes what? I mean, now when I do this change, what happens? It's x of k, fine. And I have e power j, omega is k times 2 pi by n times n, right? And what happens to integration? Summation, what variable I will sum it? Okay. Is that okay? And finally I have d omega. What happens to d omega? Yeah, here in continuous thing I have d omega that could be as small as 0. Here the step with which I am incrementing omega is what? My d omega is 2 pi by n. So that kind of cancels things. So I'll just get 1 by n here. Cool. So this is what typically we need to do in practice. And I mean, as of now, it seems like there is no particular relation between this nr, which is the record length or the number of data points you have captured in time domain, and n, which is the number of frequency points at which you are calculating the spectrum. But looks like there is no relation, but let's not jump to any conclusion. So here, can you tell me what is x of capital N plus n? I'll do the same thing, summation over k, x of k, e power j k, 2 pi by n. I'll replace small n with small n plus capital N. You will find that, I mean, this n cancels with this guy. You will have e power j k 2 pi, which is just 1. So we'll end up with this fellow alone. That is same as x of n. So now you see it's periodic with n. Again, this shouldn't be surprising at all, right? Remember that when we took a signal and sampled in time domain, what did we observe in the frequency domain? After sampling, what happened to the spectrum? We had some periodic repetition in the frequency domain. Here, where are we sampling? In which domain are we sampling? We are sampling omega. We are sampling in the frequency domain. So we expect periodicity in time domain. That's what is happening. It's nothing significant, so let me mark it here. Whenever you sample in one domain, you expect periodicity in the other dual domain. There is fine. So let's ponder over this fact for a moment. What this statement means is that if I take a sequence x of n, record it for total of nr samples. So let us say it's something like this. Okay. Again, this is all discrete time samples. I don't want to spend time drawing like this. So I'll draw it like a continuous time sequence. So I have a total of, mark it like this, nr samples. What I do is I try to find its spectrum at k 2 pi by n, where capital N is the number of points at which I am computing the spectrum. I get some spectrum, and then from this I reconstruct what would have been my time domain signal. Let's call that some x tilde or something. and here I find that the sequence is periodic. That is, this is the original thing, 0 to NR minus 1 whatever, and then I have periodic repetitions on, say this is one thing, I have something at every n to 1 it keeps repeating.
Just like the convolution we had.
It's not, what's convolution?
Time domain.
Yeah, I mean, yeah, there you got it because you convolve with impulse time, but the idea is same. Sample in one domain, you expect periodic repetitions in the other domain, right? So remember here, this was total of NR samples. Here, this is N. So what have I inherently assumed for N and NR? N is greater than NR, right? So this is what it is. Let me write it here. If I choose the other way, what happens? Yeah, it's same as aliasing, right? Whenever you sample in one domain, if you don't sample it, let us say sufficiently enough, you expect aliasing in the other domain. It's again due to the fact that you have repetitions in the other domain, right? So if you choose the other way, you will have this and you are screwed. Fine. So this is not something you want to do. So you always try to do this. Okay. So again, here it can be n greater than or equal to nr. Okay. But let us say you choose n to be greater than nr. What will happen is, when you reconstruct the sequence, I'll have this guy samples. You'll have zeros here, and then it will start. Right? That's what it means. So now you see that in between points are all zeros. So instead of wasting with zeros, you could as well fill with your original sequence. So you can choose n to be equal to nr. Is that logic okay?
So if there is aliasing, then the signal, the output at that point will be some of those two.
Some of those two, yes. We can do this actually and see. So basically, other way to make sense of this is that, maybe that is better. See, this statement can be reinterpreted in the following way. The statement is this: when I record for NR samples, find the spectrum for n points, and then reconstruct it, I see that my reconstructed sequence is periodic with this n. So the other way to visualize it is this. So whenever I do this, what happens is the following. I have some sequence which is NR long. The analysis inherently assumes that I have a periodic signal that is obtained by repeating this guy every n samples, and then the spectrum of this periodic sequence is what is computed. Because it doesn't make a difference for both, right? So this is another way to say the same thing. Okay. Now remember, in our cases we are dealing with sinusoids, and technically a sinusoid goes from 0 to infinity. But what you are doing is you are probably capturing the sinusoid for, let us say, one cycle like this. Again, it's all discrete time. Okay. This is NR points. Now if I choose my n to be greater than NR, what it means is that while computing the spectrum, it is inherently assumed that this portion is going to repeat on either sides with the periodicity of NR samples. So what will happen after this point? It will repeat. So we'll eventually have a signal like this. Okay. But that's not what you want. You want a signal that looks smooth and continuous like this. So that is why you choose this point to be equal to this. That boils down to the fact that you choose my record length to be equal to the number of frequency points at which I am computing the spectrum. Just a long way of saying the same thing, but anyways. So let's just make this change and wrap up today. So this was the modified thing we saw. Here the only change I will do is the record length will be same as n, which is the number of frequency points. So let me, I'll probably copy and paste it here and wrap it up. So the only thing is this. Okay. and I'm sure you guys have seen this earlier, hopefully, or not, I don't know. This is called as discrete Fourier transform. Have you guys seen this earlier or first time? Seen this somewhere? So bottom line is DFT is not something that is there so that we want you to learn something new additionally for asking questions. It is a natural evolution because of practical difficulties in computing discrete time Fourier transform. If this were easy to compute in practice, you don't need to have this at all. The fact that I cannot compute this for all omega and the fact that I can't record for infinite samples naturally leads me to this path, and that's what is called discrete Fourier transform. So bottom line, when you do this discrete Fourier transform, my omega axis is discretized now. I'm computing the spectrum at discrete frequency points. And what is the spacing? If I take an endpoint, let me do this. This is called endpoint DFT, again for obvious reasons. So this spacing is 2 pi by n. And jargon to remember is these points, they are also called as frequency bins. I have no idea why it's called like that, but anyways, for some reason they call as bins. So let us say I take a kth point, or I will say kth bin. What would be the corresponding discrete time frequency? Remember that the spacing is 2 pi by n. Just k. See, this is 0, this is 1, 1 is 2 pi by n, 2 is 4 pi by n. Similarly, k will be k times 2 pi by n. So, right? And let us say the discrete time sequence is originally obtained by sampling it at a sampling frequency fs. What is the corresponding continuous time frequency if I were to map it? This is the discrete time frequency, right? Can you tell me the corresponding continuous time frequency if the sampling rate is fs? Or what continuous time frequency I should have sampled at fs to get this frequency? Huh? No, if I sample at fs, no. Okay, remember, if I have a signal at fs, after sampling, what is the discrete time frequency? 2 pi. So basically fs maps to 2 pi. Now tell me, what will this map to? K times fs by n, right? That's all. I mean, this is a thing to remember. Fs maps to 2 pi, everything is a linear scaling of. So this is the frequency bin, and you do this. So the first change is this: you sample the frequency axis, and the second change is you don't do the summation for infinitely long time. You do it for n samples. So which means what essentially you are doing is the following: you take the sequence x of n, which might be spanning from 0 to infinity. You limit it only for n samples. That can be treated like multiplying it with a sequence of ones, n ones and all zeros. And then you take the Fourier transform at k times 2 pi by n. Right? So this typically is called as a rectangular window. So this I will say it's rect n of n to signify that it is having n ones. So the bottom line is my DFT, or I will say endpoint DFT, is basically the discrete time Fourier transform of a truncated sequence of my input sequence. I truncate it for a total of n samples, that is, I am making the record length finite, and I am computing the spectrum not at all frequency points, at just k times 2 pi by n, where k goes from 0 to n minus 1. Is that okay? Fine? Good.
Sir, here DTFT are we truncating, like first we are truncating the sequence for k.
Correct.
Then like we are then repeating that
Yeah.
Like,
Correct. Yeah, I mean, the point is whether you find the DFT for that end sequence alone. When you find it, it is inherently assumed that you have a periodic sequence.
but in DTFT,
DTFT there is nothing, yeah, because you are doing for infinity, so there is no issue. Okay, cool. And yeah, I mean, some of you do this. Typically in the olden times, or I would say if you choose the number of points to be a power of 2, it turns out there are some efficient algorithms to compute this spectrum called as fast Fourier transform. You might have heard as FFT. Of course, this made a lot of sense 50 years back, where computation was very costly. But right now, with the power of computation you have at your disposal, there is no need to choose n to be a power of 2. You can choose it to be anything. You can choose it to be a prime number or whatever you want. But sometimes for legacy reasons, we might still choose to be a power of 2. But FFT, I mean, yeah, as of now, for normal calculations, it doesn't make a difference. Okay, so yeah, so let me just finish up the discussion. Again, let's all rewind and recollect where we started. We wanted this. We wanted to find the signal to quantization noise ratio. Ideally, if I could have done this, I am set. But as we saw, I cannot find discrete time Fourier transform. So we'll have to do discrete Fourier transform. So let me actually take this and then show you this and we'll wrap up. Okay. So here I computed the power spectrum like this. Now with discrete time, I'll have the same thing, power spectrum computed as 1 by n expected value of mod v of k square. That's all. Same thing. If I do this, if I plot one-sided PSD, in omega it was going from 0 to pi. Here I will have k. So what will be the range I will have? 0 to 2 pi was split as 0 to n. Now I am looking at, pi. Huh? No, is clear? I mean 0 to 2 pi was split as n points. I am looking at only a range till pi, n by 2. Okay. So we'll have discrete points like this. I expect that the sinusoid will show up like an impulse as before. These are all discrete points, by the way, right? And all the other quantization noise will have a flat spectrum like this.
will we go till n by 2 or n by 2?
Technically, pi is n by 2.
Or pi is n by 2?
Yeah. So whether you do it till n by 2 minus 1 or
0 to 2 pi, right?
yeah, so this is basically a slightly this thing. If you it is up to you. Typically, you also show n by 2 because you can show the spectrum till fs by 2. So you show it till n by 2, right? Okay. Yeah. So the last thing again from here now we can see strength of this discrete time impulse will give the signal power. How can I find the noise power, quantization noise power? Huh? I mean strength of this one gives me signal power as usual. For finding the noise power, what can I do? Area of what? Yeah, area of what? You sum this whole thing and then subtract this. That is basically saying I am taking sum of. So you just exclude the point where the signal is and then sum the rest of the frequency bins. That will give the noise power and that will give you SDR. So in the next class we will see if this is what happens or if there are some issues. So I'll stop here. I'll just give you a brief summary of what we looked today. I thought that might help you recollect this long class. So first takeaway is this. Hold on. Yeah. We saw for an n-bit quantizer, the step size is 2 Vref by 2 power n. And we saw this quantization noise we model as an additive error that is getting added. Its range is from minus delta by 2 to plus delta by 2. And to make our life simpler, we started to make some assumptions. One was the fact that this guy was a random sequence as a uniform PDF. And from its PDF, we saw that the power was delta square by 12. And then we saw this maximum signal to quantization noise ratio was 6 times the number of bits plus 1.76. And that gives one way to characterize an ADC. And we saw this has to be done in frequency domain. which requires you to know power spectral density. And in that process, we decided to assume that quantization noise as a white power spectral density, right? And you compute the power spectral density like this in principle: magnitude squared of Fourier transform, expected value of this divided by n. But in practice, DTFT had these issues. This is the fact that omega is continuous and you need to store for infinitely long samples. Simple solution is you sample at discrete frequency points like this and choose a finite record length NR. And when you do this, we saw the reconstructed sequence was periodic with n samples. So we usually assume these two guys to be same, and that gives you discrete Fourier transform, right? Yeah, so bottom line, DFT can be thought of as taking your infinitely long sequence, truncating it for n samples, finding the discrete type Fourier transform at these frequency points. Is that okay? So stop here, we'll continue, please.